Welcome back to the class of differential equations with matrices. And in this part, we are talking about the Laplace transform. It's a topic in chapter 8, section 8.1. And we already covered most part of it about the Laplace transform. And specifically, I want you to take a quick look about those formulas. Okay, these are the Laplace transform formulas. The first formula is simply says for any power function in the fashion of t to the n, we are going to have the transform as n factorial over s to the n plus 1. This really it is for the family of power functions. Then remember we have exponential functions. So accordingly, the Laplace transform of e to the at is 1 over s minus a. And also we have trigonometric functions. We only consider cosine and sine, okay? Cosine in the fashion of kt, sine in the same fashion kt. So accordingly, we do have the Laplace transform for these. And also we do have the combination of exponential and the power function, and the transformation of exponential and the cosine, transform of the exponential and the sine. Somewhat they are very similar rules. I hope you see the pattern, and they do follow those strict patterns. And somewhat like you look at the exponential term, okay, t to the n, it is n factorial over s to the n plus 1. We have kind of same kind of thing, right? Because of the exponential term, the s, it is being translated into s minus a. And then look at e to the at times cosine bt. This is the transform of cosine kt only. And then with the exponential term, this s, it is being translated into s minus a squared. Similar situation for the Laplace transform of e to the at times sine bt. Actually, I guess, well, I'm just going to keep the notation as they are. This part is a k and this part is a b, and really the same thing. Okay, you could interchange k and b or keep all the notation the same way, same fashion. Okay. And the Laplace transform, there is a summary as a table on the textbook on page 472. Okay, and also we have some examples. I think we did those examples in my other video. Okay, and also another important thing, quite an important thing for the Laplace transform. Laplace transform, it is defined as improper integral. It is integral transform, but anyway, it is considered linear. The reason we consider the transform is linear because we do have the following properties. This should be considered as the transform of the sum of two functions. It turns out to be the sum of two transforms. And the next property, it is about the scalar multiplication. The transform of the constant times the function, it is the constant times the transform of the function. Laplace transform, it is a linear operation. Okay. And also, more importantly, really for this part, we are going to work with the inverse of the Laplace transform, the inverse Laplace transform. Look at all of the formulas. Roughly, we can say the Laplace transform, it is converting a function of variable t into a new function of variable s, right? From t to s, t to s. They are all in the situation t to s. Then accordingly, the inverse transform, it is the transform from s to t, and this is what I put in writing. Okay, the inverse transform, it is the function of s going back to function of t, and certainly these are different functions. So I'm using, for the s, I'm using notation uppercase f, and for the function of t, I'm using lowercase f here. Okay, and now basically all the formulas we just reviewed, the Laplace transform can be reversed into the inverse transforms. So accordingly, if you have a fashion like this, the Laplace transform of inverse transform of something of s, n factorial over n plus s to the n plus 1, that tends to be t to the n. That is the transform from s to t, right? The inverse Laplace transform. And specifically, if we are having n equals 1, actually this is the case n equals 0. Remember, n equals 0, 0 factorial is 1. Okay, 1 over s, the Laplace transform, it is 1. Like we calculated before, the Laplace transform of 1 is 1 over s. So the inverse transform of 1 over s, it is 1. And also the inverse transform of 1 over s squared, this is just case when n equals 1, so you choose just t. The inverse transform of 1 over s cubed, this time you want to be a little more careful. Okay, a little more careful. According to the inverse transform, this really to match the formula, we really needed to have 2 over s plus 1, 2s to the power of 2 plus 1. Then that would be t squared. I mean, there's 2 here. But the Laplace transform is linear. And also I have a small comment you may want to know. The inverse Laplace transform, it is linear too. So what I did here is, indeed, it could make up 2 on the top as part of numerator. And then you got this extra 2. So you take out another 2 in the denominator. Okay, so that tends to be 1/2 times 2 over s cubed. So accordingly, the inverse transform, it is t squared over 2. And similarly, the Laplace inverse Laplace transform of 1 over s cubed. Basically, we are matching the formula s to the power of 3 plus 1, but we do need to have 3 factorial on the top. So I pretended to have 3 factorial on the top, then I need to have another 3 factorial in the denominator. Certainly the 3 factorial on the top, it goes with this formula. The 3 factorial in the denominator, it stays there. Okay. The reason we can keep the 3 factorial as it is because the Laplace transform and the inverse Laplace transform both are linear. The inverse Laplace transform. And certainly we have more formulas about inverse transforms, right? And we have more formula about the Laplace transform. So we are having more formulas for the inverse Laplace transform too. So this is the inverse transform of 1 over s minus a. It tends to be e to the at. The inverse transform of 1 over s minus 3, it tends to be, it's the case as a equals 3, e to the 3t. The inverse transform of 1 over s plus 1 is s plus 1. Because you look at the formula, we must have something like s minus number. But we could minus a negative number, right? So this tends to be the situation s plus 1. So accordingly, the inverse transform, it is e to the negative t. Still, it does fit the formula, e to the at here, okay. A is negative 1. And similarly, we may have the inverse transform involving with sine and cosine. These are just directly copied from formulas. Okay. And also, I would say you want to look at the other cases somewhat more complicated. The inverse transform involving with power function and the exponential function, trigonometric function, and the exponential function. Okay, and then remember, I said that when you work with the Laplace transform, basically the exponential term plays the role like to translate the single variable s into s minus a. A very similar situation for the inverse Laplace transform. If you have s being translated into s minus a, then you must have the exponential part for the inverse transform here, okay? Exponential, because all of the s are being translated into s minus a. Basically, that's it about Laplace transform and inverse Laplace transform. How about let's take a little more examples about the inverse Laplace transform, because I say inverse transform is more complicated. Okay, so indeed I believe this is example 6 on the textbook. What we are given here is a function in terms of s, okay, it's a rational expression, okay, a polynomial divided by polynomial. We want to find out the inverse Laplace transform. And then, as I'm saying, not a single formula will match any of those things. Okay, not a single formula will match this rational expression here. And what I figured out here is, well, we needed to use some old knowledge, the so-called partial fractions. This bigger fraction can be separated into two fractions. And it will, if I go through the details of partial fractions, it will take another a class or two. So I'm going to skip the discussion of partial fractions. If needed, do let me know, and we'll try to find some time just to discuss partial fractions. So using partial fractions, I realize this entire fraction it comes from those two relatively small fractions. Okay, and then 2 over s minus 1, I say we can take it because the Laplace transform and inverse transform both are linear. We can take out the 2. So it tends to be 1 over s minus 1. 1 over s minus 1, okay. And then another issue is about 1 over s squared plus 5. And you want to match the formula very carefully. I'm seeing a trigonometry will match here. Okay, it is for the sine part, k is a constant, s squared plus k squared. We are having s squared plus 5. So you want to make this 5 as a perfect square. So that's square root of 5 squared. And then if you want to see the formula carefully, you need to have square root of 5 on the top too. So this is what I did. I do have square root of 5 on the top. This is what I created. It's not in the original problem. So to keep this fraction balanced, unchanged, I also, at the same time, I got another square root of 5 in the denominator. And again, because the Laplace transform and its inverse both are linear, so which allows us to take out the transform of the first part and the second part separately, each multiplied by a scalar quantity. So I guess this may look a little complicated, right? It's fair to say. Okay, the Laplace transform. Make sure you do understand those formulas very well. Laplace transform and the inverse transform. Let's do one more example. It is still on the textbook. I believe it still does require partial fractions. Okay. So this time, what we are given here is we are having a function of s, f of s. Okay. In this fashion, still not a single formula would match. And also, I want to know here is the situation. Okay. For the previous one, the denominator, it is a product of two polynomials, a linear and a quadratic. And this time, the denominator cannot be factored. But what I see here is we always can make two perfect squares out of this denominator. S squared plus 4s plus 4, that will turn out to be a perfect square. And then when you have this plus s, basically you want to minus s in the end. So 13 plus 4, then 13 minus 4, which is just 9. Or consider the other way, you can consider 13, it is split into 4 and 9. So the denominator turns out to be two perfect squares. Two perfect squares. Okay. And then the reason I want to have two perfect squares as denominator, look at those transforms. The transform involved with exponential and trigs. Okay. Each denominator is a sum of two perfect squares. Okay. So considering the denominator as a perfect square, I separated the fraction into two. And also remember this s, normally we expect this s squared, but we are having s plus 2 squared, which means s it is being translated by the number -2 or by plus 2 there. Okay, if you consider s minus formula s minus -2. Okay, so I try to match the numerator with s plus 2 too. But you see, originally I'm having the numerator at s plus 1. When I change this s plus 2, which means I have to minus 1 again to keep the numerator at the same as the original one. Okay. And then I figured out the fraction it is separated into two. It's kind of like a partial fractions, but it's really not. Okay, in this case, denominator cannot be factored. And indeed, the denominator turns out to be the sum of two perfect squares. And in that case, each would match these formulas. These two formulas, e to the at cosine bt, e to the at sine bt. So this is what I got, realizing those two transformation formulas, inverse transformation formulas, I get the inverse transform as e to the -t, s plus 2, s plus 2. And that will match cosine 3t. And also for the second part, one-third state, because inverse is linear, the one-third state. S plus 2 is being translated into, S is being translated into S plus 2 or S minus -2. So the exponential term is the same, e to the -2t. But the numerator is 3 matching the other perfect square, 3 squared in the denominator. So that's a sine 3t. So overall, this is the discussion of Laplace transform and its inverse. Laplace transform and its inverse in the section of 8.1. 8.1. Next time, mostly we are going to use the inverse Laplace transform to solve differential equations. Or I should state it precisely. To solve differential equation, it does require both Laplace transform and the inverse. Thank you for watching. See you next time.